Weak acids, concerning ourselves with equilibrium ionizations. All of our previous discussions thus far have been based on strong electrolytes, specifically strong acids. A strong electrolyte has near or 100% dissociation or ionization. In these kind of solutions, we treat the solution as being completely ionized. For example, a 1 molar solution of hydrochloric acid, HCl, would be treated as being a 1 molar solution of H+, and a 1 molar solution of Cl-. The solution pH then is based on the concentration of the acid. So if my acid is 1 molar for a monoprotic acid like HCl, the pH would then be the negative log of 1 molar. Weak acids and bases, however, only slightly ionize. Usually the ionization in a weak acid or weak base is less than 5%. The concentration of hydronium then which comes from the acid will not be equal to the acid molarity. Most acids and bases that we experience are going to be weak, and they will have to be represented by an equilibrium expression. For example, if we look at carbonic acid, H2CO3, carbonic acid dissolved in water will react with the water to protonate it, forming hydronium, the same way that hydrochloric acid as a strong acid would. However, rather than the entire equilibrium lying towards the right-hand side of the expression, something like carbonic acid will have an equilibrium that goes both ways and actually lies predominantly to the left of the expression. In the same way, acetic acid will ionize in water, forming acetate, where the carbonic acid forms hydrogen carbonate. And both of these expressions will lie towards the left-hand side. Now, the degree to which they'll lie towards the left-hand side depends upon the individual nature of the acid in question. Looking at Kc for weak acids then, there are two different types of acids. We have monoprotic acids and polyprotic acids. Monoprotic, as it sounds, have a single proton. Polyprotic have more than one. These can be diprotic acids, which have 2 protons, triprotic acids. Generally, it's going to be one of those two. So looking at weak monoprotic acids, something like acetic acid ionizing in water to form acetate and hydronium. The equilibrium expression for this would be the Kc value equal to the hydronium concentration times the acetate concentration divided by the acetic acid concentration times the water concentration. Remember that water, as a pure liquid, has an activity of 1, so our overall equilibrium expression becomes our Kc value equal to hydronium concentration times acetate concentration over acetic acid concentration. Generically, this equilibrium expression for the reaction of an acid can be expressed as Ha plus water yields hydronium plus the deprotonated A-. The Kc for this expression then is hydronium times the conjugate base divided by the acid. A Kc for an acid is called a Ka, or the acid ionization constant. This is also sometimes referred to as a Ki. As an example, if I have a dilute solution that has an acid concentration of 0.049 molar, the H+ concentration and the A- concentration have 8.4 times 10 to the minus 4 molarity overall. This is for a monoprotic acid, remember, because we are deprotonating on a 1-to-1 basis between our H3O+ and our A-, we should have equal concentration of both the H+ and the A-. So based upon these molarities, find the Ka value and then the negative log, or pKa value. The Ka value will represent 8.4 times 10 to the negative 4 for the H3O+ concentration and 8.4 times 10 to the negative 4 for the A- concentration over the acid concentration of 0.049. This expression gives us a Ka value of 1.4 times 10 to the negative 5. Taking the negative log of that to find pKa gives us 4.85. Now, Ka values are useful. Ka gives us information about the relative acidity. A high Ka value will have a high degree of ionization because it will lie towards the right-hand side. Conversely, a high pKa, or negative log, will have a low acidity. The larger the number, the smaller the pKa will be. The smaller the number, the bigger the pKa will be. That's the nature of logs. So we can use the Ka value and any sort of acid molarity we know to determine pH, in the same way that we determine Ka value from relative concentrations. So for example, a solution of hypochlorous acid, HClO, being ionized in solution to form hydronium and the hypochlorite ion. Ka value will be the hydronium concentration times the hypochlorite divided by the concentration of hypochlorous acid. Given a pKa or a Ka value, we can use our equilibrium expressions, ICE, initial change equilibrium, to solve for the hydronium concentration. So for example, if I want to calculate the concentrations of all species and find the pH for a 0.1 molar solution of hypochlorous acid with a Ka value of 3.5 times 10 to the negative 8, I would start with my equilibrium expression. My initial concentrations are 0.1 molar for the hypochlorous acid, an activity of 1 for water, a 0 concentration for hypochlorite because nothing is yet ionized, and approximately 0 for hydronium because 1.0 times 10 to the negative 7 is very, very, very small compared to 0.1. So in relation to 0.1, it's approximately 0. The change then loses X amount of hypochlorous acid and gains X amount of hydronium and hypochlorite. The overall equilibrium concentrations then are 0.1 minus X and X respectively. Plugging this into our equilibrium expression, our Ka value is 3.5 times 10 to the negative 8. We have H3O plus at X, ClO minus is X, and HClO is 0.1 minus X. Now given that 3.5 times 10 to the negative 8 is a very small value, we can assume that X is negligible in relation to 0.1. As long as X is less than or equal to 5% of 0.1, we can hold that our assumption is valid. So solving for X is the square root of 0.1 times 3.5 times 10 to the negative 8, which gives us a value of 5.9 times 10 to the negative 5. If I compare this against 0.1, as a percentage is only 0.059%, which holds our assumption to be valid. The concentration of OH minus then will be our Kw divided by hydronium concentration. 1 times 10 to the negative 14 divided by 5.9 times 10 to the negative 5 gives us a hydroxide concentration of 1.7 times 10 to the negative 10. Hydronium concentration is 5.9 times 10 to the negative 5. The hypochlorite concentration is the same because they ionize in equal amounts. Our hypochlorous acid concentration is assumed to have not really changed at all. And our hydroxide concentration is 1.7 times 10 to the negative 10. If we take the negative log of our hydronium concentration, we get a pH value of 4.23. Notice that for weak monoprotic acids, such as generically HA going to H3O plus and A minus, the concentration of H3O plus will equal the concentration of A minus. HA will equal the solution molarity. So if I want to calculate the percent ionization of a solution with respect to the hydronium concentration versus HA, if I have a hydronium concentration of 5.9 times 10 to the minus 5 molar that we just calculated, our hypochlorous acid at 0.1, taking 5.9 times 10 to the minus 5 divided by 0.1 as a percentage gives us 0.059% ionization. Dilute weak acids are primarily non-ionized. So, for example, acetic acid, a 0.1 molar solution, has only 1.3% ionization. Usually these ionizations will be less than 5%. Dilute strong acids, however, are primarily ionized. Hydrochloric acid will be primarily 100% ionization for a 0.1 molar solution. We can understand the relationship better if we look at a pKa value. A strong acid, which has a very high Ka, 1 times 10 to the 8, has a low pKa value, negative 8 in this case for hydrochloric acid. A weak acid, however, which has a very low Ka value, has a high pKa value. Acetic acid has a pKa value of 4.74. So the larger the pKa value, the weaker the acid. The smaller the pKa value, the stronger the acid. Now our small value assumption sometimes will fail in these situations. For instance, if I look at a solution calculating hydronium concentration for a 0.1 molar solution of chlorous acid, this has a Ka value of 0.011. We write our expression. Our initial concentration will be 0.1 for chlorous acid and approximately 0 for hydronium and chlorite. The change is negative X and then positive X respectively for the two on the right hand side, giving us an equilibrium expression of 0.1 minus X and then X and X. Plugging that into our Ka value, our Ka is 0.011, our values of X are x on top, multiplied together, then divided by 0.1 minus x. If I assume that x is negligible, then I have x being the square root of 0.1 times 0.011, which gives us 0.033. If I express that as a percentage versus 0.1, it is 33% of 0.1, which is much greater than 5%. So this means that our assumption isn't valid. We then have to use the quadratic formula and the quadratic equation of this process in order to get the x value. If I establish a quadratic formula for this, it comes out to x squared plus 0.011x minus 0.0011 equals 0. Plugging that into the quadratic equation will give us either negative 0.039 or positive 0.028. Because we cannot have a negative concentration, we select the latter of the two, giving us a hydronium concentration of 0.028 molar versus the 0.033 molar we would have got by assuming the x is negligible. That's a 15% difference, which is fairly substantial. We can also have our small value assumption fail in changes where we have very weak acids. For example, ethanol can function as a very, very weak acid with a pKa value of 15.9. The Ka value for that then is 1.26 times 10 to the negative 16. Now this does fall within our rule of 10 to the negative 3 or less, so negative 3, negative 4, negative 5, whatever. However, it is so small, it becomes important. In a 0.01 molar solution of ethanol, we have an initial concentration of 0.010, initial concentrations of hydronium hydroxide assumed to be 0. Our change will be minus x plus x and plus x. Plug it into our equation. We get 1.26 times 10 to the minus 16 equals x over 0.010 minus x. If I assume x is negligible, then x is calculated to be 1 times 10 to the negative 9. Now remember that the concentration of hydronium in pure water is 1 times 10 to the minus 7. So the calculated concentration of hydronium is less than that of pure water, which isn't possible because the amount that is from pure water will be there. So in this case, the hydronium concentration is actually the hydronium concentration of pure water. This means that solutions of things like ethanol, even though they are very, very weak acids, tend to basically be neutral solutions. Any instance where I calculate a hydronium concentration of an acid that is less than the hydronium concentration in the solvent, the solution hydronium concentration will be the hydronium concentration of the solvent.